So okay, so is this screen visible? My voice is audible?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, very good. In
Yep.
that case, so let's just quickly review. We were doing this Cauchy's integral formula. Extension of that is what is written at the top. And then in the last class, we did the power series expansion. And we mentioned this is one of the highlights of complex functions, that now you can talk about the series expansion without worrying about whether the higher order derivatives are analytic or not. And that's the case for analytic functions in complex functions. Now, we try to expand it around the point when it is not a singularity, and we also try to expand it around a point when it's a singularity. Yeah, so we did two kind of series expansion. One we called as the Taylor series expansion, another we call as the Lorentz series expansion. Please remember one thing which is very important is the radius of convergence. Radius of convergence of the Taylor series is till the first isolated singularity is encountered, which means that radius will continue to grow, that the function remains analytic, and till it encounters first isolated one singularity, that is Z1. And in the Lorentz series, since we are expanding around a singularity, so that means that we have some sort of a punctured disk or annular region about which we are expanding our terms. So that's pretty much it what we have done. Today we are just going to continue with the same, except that now I am going to introduce what we call as singularities, and I am going to introduce only the isolated ones. In fact, the point is that we are going to take care of only the finite number of isolated singularities, not even the infinite one. Now, why I introduce singularity at this point? Since we have done the Lorentz series expansion, so several cases arise out of Lorentz series expansion. When I'm saying several cases, the first case which can arise, that in the Lorentz series expansion, we do not have any negative powers of the term z minus z naught. So if we do not have any negative powers of z minus z naught, that is around z naught when we are expanding, and no negative powers, then what does that mean? Is there a singularity which is existing? So let's just look at the form of the Lorentz series. Will there be any singularity?
No, sir.
No, sir.
There won't be any singularity. There is something else. So no singularity case. There is something else which is there, which we call as the zeros, but I will come to that quickly later on. So no singularity in this case. Okay. Now then there exists second one. So let's say we are expanding fz about a point z naught such that we have terms of the type a minus m z minus z naught raised to power m plus a minus m plus 1 divided by z minus z naught m minus 1, so on and so forth, a minus 1 z minus z naught plus a naught plus a1 z minus z naught, and so on and so forth. Now what is peculiar about this, that we have this finite value of m for which this coefficient a minus m is not 0. Yeah, so this is something like the most negative power of 1 over z minus z naught is this finite integer m, and any power which is beyond this, a minus m minus 1, a minus m minus 2, so on and so forth, all other powers of 1 over z minus z naught are 0. So this term, this guy, is the most negative power of 1 over z minus z naught. And this m is of course some finite integer. This is a case when we call that whether, first question, is the singularity there in this fz or not? Is this function
Yes, sir.
singular at
Yes,
what
sir.
at what point?
Z is equal to Z.
Z is equal to z naught. There is singularity, and this singularity, if we have the Lorentz series expansion of this form, we call this pole of order m. And if this m is equal to 1, then we call that pole of order. So if m is equal to 1, that means the most power which is non-zero is a minus 1 over z minus z naught, and all other terms of 1 over z minus z naught square, etc. are 0. The coefficients are 0. Then we call this pole of order
So one.
1, of
One.
course. Of course, right? This is called simple pole. That's the only thing. Otherwise, of course, you keep on. I mean, you can even say pole of order 1, and that is absolutely fine. So, pole is a singularity in which the Lorentz series expansion of our function fz will have finite terms having this coefficient 1 over z minus z naught. After that, all the coefficients, they will all be 0. So, this is what we call as the pole. And then there is a possibility that we cannot find m. So there is no such finite m for which Lorentz series expansion is finite m for which Lorentz series expansion is terminated in 1 over z minus z naught. What does that mean? That means that our coefficients a minus m minus 1, maybe that is 0, but then the next coefficient is not 0, such that there are infinite number of terms. So you are unable to find out any finite positive integer m for which our series, Lorentz series expansion, terminates like the previous case. And in this case, we call this kind of singularity. Of course, this is also a singularity because z minus z naught is coming in the denominator, and we call this essential singularity. So we talked about two of the singularities here. One we call pole, which is nothing but when the Lorentz series expansion is terminated for some finite values of m. And if it doesn't get terminated, then we call that singularity the essential singularity. In case if there is no term of the type 1 over z minus z naught, of course there is no singularity in that case. It is this Taylor series expansion basically. And Taylor series expansion is done for only the analytic functions. Yeah. There is one more singularity, which is seeming singularity, which is not exactly a singularity, but it looks like a singularity, even though it is not there. So, for example, let's consider a function like sine z over z. Now, this function is interesting. Why? Because if I ask you what does this function do at fz at z is equal to 0, then what will you say?
Not defined.
Sir, not defined.
So this is 0 over 0. So this is not defined. Absolutely right, indeterminate. But the function seems to be of the form that z is coming in the denominator, looking like at z is equal to 0 is a singularity. Question: if a function looks like, seems like that there exists a singularity, however the function itself is not defined, then what can we say about it? Is this a singularity at z is equal to 0 or not?
So
What are
that
we
means we can remove that singularity.
Is it always possible if a function is indeterminate that you can remove it?
Sir, if the inverse terms do not go till infinity in the
The
expansion.
no, even if the inverse term exists for 1 over z, then also it's a singularity, right? Right? So there are two ways. One, you do your Lorentz series expansion about z is equal to 0 or whatever the singular point looks like, and figure out whether there exists any term of the kind 1 over z or not. 1 over z, 1 over z square, so on and so forth, any term of the kind. If there exists term of that kind, then there is a singularity. And in that case, of course, you will say that, okay, sir, there is a singularity. But if you do not find any such terms, you will say, sir, there is no singularity. This singularity, which seems to be there, but which is giving you the indeterminate form, is not a singularity. It is what we call as removable singularity. Now, this is something interesting because, I mean, in some sense, it's not a singularity. It appears as a singularity. What does the function do in these cases? I mean, that's of course interesting to see. But for our purpose, we are just going to figure out whether we can remove it or not, as somebody said it. There is another way of removing this singularity here, whenever it is a indeterminate form which comes. What is that? You use what rule?
L'Hopital's rule.
Sir, L'Hopital's rule.
L'Hopital rule, or otherwise what you are trying to see, that you will trying to find out if limit z tends to 0 fz exist or not. That's the big question which you are going to answer. And in order to find out whether limit z tends to 0 exists, you just take help from your real calculus or calculus of real variable, where you use L'Hopital rule. And you know, for generally, I mean, analytic functions, you can do that without any problem. For non-analytic functions, you do not know whether you can actually or not define it. But what do? You just apply the L'Hopital rule. How do you apply it for sin z over z?
Sir, cos z over 1. Like we take the derivatives of
So
the
derivatives of the numerator and denominator separately. So limit z tends to 0. In general, this can be z naught, but okay, here in this case, it is cos of z over 1, which is
1.
1. So limit z tends to z naught fz exist. And hence you say that the z is equal to 0 is a removable singularity in this case. So what we have done in essence, using the Lorentz series expansion itself, you can actually figure out, because does somebody remember the Lorentz series expansion of sin z? It is, I mean, something similar what you have found in your real calculus. Sin z is an entire function, so it's a reasonable one. It's a Taylor series, or in fact a Maclaurin.
By 3 factorial.
Great. Plus z5 over 5 factorial. Thanks. Is good. And this guy becomes what? 1 minus z square over 3 factorial plus z4 over 5 factorial, so on and so forth. Does this have any term of the kind 1 over z?
No.
No, sir.
No, which means that this z is equal to 0 is only an apparent singularity, but it is not an actual singularity. You can figure out from the Lorentz series expansion. So Lorentz series expansion will allow you to figure out whether a singularity is there or not. If the singularity is there, is it a removable one? Is it a pole of some order, or is it an essential singularity? So now let's just have a very quick example. Sin z, any singularity?
No, sir.
No, sir.
No, sir.
Okay, good. Sin z over z we have already encountered, and we call this the removable one at z is equal to 0.
0.
Let me just continue. What about sin z over z square?
Sir, singularity at z equals 0.
What is that singularity?
Sir, a pole.
Simple or any order?
A simple pole.
So, do all of you agree?
No, sir.
Yes, sir.
No, sir. Yes, sir. All you have to do is to just put 1 over z square here and just multiply it with sin z. See what happens. What's the most power of the term 1 over z? What is the most power of this?
1.
1.
One.
So you can find out that there exist finite terms only, and the most power is 1, which is simple pole, right? Now, what about if I just ask you to figure out sine 1 over z? What kind of series expansion you will get?
Sir, infinite terms of the form of 1 over z.
So this will be 1 over z minus 1 over z cube 3 factorial plus 1 over z raised to power 5 factorial, so on. About z is equal to 0, and you will find that there will be infinite terms. So there is no way you will find any finite place where the Lorentz series will be terminated, and hence this singularity will be
Sir, essential.
at
Essential symmetry.
essential at.
Z is equal to 0.
Okay. Okay, good. So this is how we figure out our singularities, just by having our Lorentz series expansion, and that is why I reserve this topic till this point. By the way, one homework: how to figure out singularity at z tends to infinity. Does somebody remember? Does somebody remember? So in the entire z plane I am not talking about. If somebody asks you to figure out singularity at z tends to infinity, what do you do? So instead of solving for fz, you solve for f1 over w, where w is another complex variable, and then you check this f1 over w at w equal to
0.
Zero.
0.
right. So when you check your function 1 over w at 0, then it is similar to checking the fz at z tends to infinity. In fact, at this point of time, I just briefly mentioned, let me just mention it, that thinking about infinity in the complex plane is also not very simple, because you have an Argand diagram with a plane. So when I am asking about infinity, so okay, let me just draw it here. So you may ask me, sir, from where are you talking about from infinity? I mean, we are coming up or going to, because it looks like that I can go to infinity in various directions. Even though 0 seems to be single point, but infinity seems to be many points. And in fact, infinite many points are infinity. So what is exactly that infinite many points at infinity will be just understood by looking at a single point, which is w equal to 0. And comes the concept of, you know what? Stereographic projections. I am not going into that detail, but it is a very interesting idea to think about infinity in complex plane, which is generally understood in terms of a stereographic projection, where we can see that how we can translate an infinite point into something which looks like a single point. Although it clearly appears that there exists infinite number of infinite points. Yeah. So that's something interesting. Those of you who wants to read it, I mean, I would again recommend Balakrishnan to at least have a go at that. Okay. Zeros. Sometimes zeros are very important or interesting, particularly if you think about the functions pz over qz. Think about a function like this. So if there exists a function like this and I ask you to find out singularity of fz, what you can do, that you can find out the zeros of qz and quickly tell me that if pz does not have any singularity, which is, let's say, if it is a polynomial, and if you know the qz, the zeros of qz, then you know the singularity of the function fz, and hence zeros also become very important in a complex analysis, and it is pretty simple. So think about it. For example, what we are interested in finding out, where this function becomes 0. That's the question basically. Yeah. And there exists something very similar to what we did in the pole. Let fz be analytic at z is equal to z naught. we say that it has, this function has a 0 of order m at z is equal to z naught if and only if there exists another gz which is analytic and non-zero at z naught such that fz can be written as z minus z naught raised to power m times gz. So if I can write down my function fz equal to z minus z naught raised to power m times gz, then we say that the function fz has a 0 or a root of order m. And please see that this is IFF, which means if and only if. So I do not need to think about anything else. Necessary and sufficient. Yeah. So quickly, if I want to, if I ask you, fz given as z square minus 9, does this function has 0? If so, what will be the order of that? How will you figure out? So you will do what? Can you write it in this form?
Z minus Z plus
So
3
z minus 3, z plus 3.
into 1.
Fine. So this is 0 of order 1. Okay, tell me this one. Fz is equal to z cube minus 8. Does this function have 0? If so, what is the order?
There is 2 of which has the order 3.
This guy has, okay, what you are saying, 0 of order 1 at, okay, here I should have written at z or z naught equal to 3. Here you are saying z naught is equal to 2 and order
1.
1, sir.
1, 2, 3. How do you decide on that?
So the identity
Sir, a cube minus b cube.
Okay. Okay. The simplest thing, if you can think about, let's just go ahead with this. If I have z minus z naught, that means that 0 of order 1, gz, yeah, and I take f prime z, what is the result?
So g of z plus z minus z naught g dash z.
G of z, and let's put it at z naught. So g at z naught and plus
Plus z
Z
minus z
minus.
naught g dash z.
plus z minus z naught g prime z, right? And I am putting at z equal to z naught. So what happens to this term, the second term?
0.
So it goes to
0.
0.
This guy goes to 0. So all you need to check is g of z 0. And what is the property of this g of z? That this guy should be non-zero at z 0. Yeah. So all you need to check that if the function which turns out to be this z plus 3, or in terms of your identity, let me just try to write down z minus 2 times what will be this z square plus
Plus 4
4
Plus
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 2z.
4z. No,
you said
yes, sir,
2z.
2z. 2z, 2z.
2z, z square plus 2z. So all you need to check whether this remaining guy is non-zero at z is equal to 2 or z not equal to 2 or not. If it is non-zero, then this guy is done at this point itself. You can try to think about what would be the case if fz is equal to, so I'm sorry that I'm writing on the same page, but unfortunately I do not want to go. So okay, I will go in the next page soon. If fz becomes z minus z square gz and I take f double prime z and then I say at z is equal to z naught. So for this guy, the next guy, fz is equal to z minus z naught square gz. What should be this property of gz? Is it again you have to think about only g z naught, or you'll have to think about z prime and g double prime, etc. at z equal to z naught?
Only.
Sir, we'll have to take double prime in that case.
Okay, very good. You'll have to take double prime. So this is what we are taking, double prime. So double prime, are you going to worry only about gz naught, or you will be worried about g prime, g double prime? So those
I
are the
guess
questions.
only GZ node.
The GZ not.
So you will find that this is the only function which, if you figure out that it is non-zero, so whichever derivative you will find out to be non-zero, correspondingly you will be able to find out the order of the zero. So finding out order of the zero in the problems when we have a function which can be written like this is basically figuring out taking the derivatives of this fz and figuring out for which of the derivative there exists gz not equal to 0. So that is all we want to find out. Which derivative of fz is not equal to 0? Whichever derivative you will find out is not equal to 0 will give you the idea that that is this zeroth order. Yeah. So this is how we find out the zeros. And I have told you that these zeros also become important whenever you have a polynomial function. So questions up to this point, and we move further.
So what is the answer of that question? Z cube minus 8.
Oh, good point. You have found out, right? So if you take first derivative f prime z, if you take first derivative, one thing you can find out that way, or otherwise you have written it z minus 2 into z square plus 4 plus 2z, right?
Yes.
You just put z naught is equal to 2 in the remaining function, which is z square plus 4 plus 2z. If it is not 0, then you already got the answer that there is only 0 of order 1. So is at z is not equal to 2, your z square plus 4 plus 2z non-zero or 0?
Non-zero.
So you have got the answer there itself. That means that whatever you have found out in this guy, this is not 0 at this one. So z not equal to 2 surely is a simple pole, because simple 0, because there exists only 1 here. So please keep on figuring out whenever you get the function, keep on figuring out that if it is 0 at z not equal to 2 or whatever z naught, then you'll have to take one more derivative, figure out at that point if this function is becoming 0. So then you will keep on finding out something like that. Okay. And this brings me to a very important one, which is what we call as residue theorem, and this is again coming from Cauchy. Oh, of course, he did a lot of, and this is just by looking at what is this a minus 1 term in the expansion of our Lorentz series. So please read the Lorentz series, which is written here, and then I have written a n. Yeah, the coefficient. What will be a minus 1? This will be this guy. 1 over
1 by 2 pi I
2
integral
pi
fz
iota.
dz.
Okay.
fz dz. And what happens in the denominator? So n becomes minus 1
1.
plus 1, 0. So this is another interesting observation coming from the Laurent series expansion only. And I should say that the C includes, of course, Z naught. So what is that? That in case if I want to do an integral over some closed path which includes Z naught, then in that case I can figure out the integral of fz dz just by finding out this coefficient, and this coefficient is what is called a minus 1.
Residue.
This is what we call as residue. So I'm not going to dwell why it is called residue because it is a rather simple thing. But the important point to note here is that residue itself can be very useful, a minus 1 term, which will directly give you integral of fz dz. So you have 2 pi I multiplied by a minus 1 and that gives you this fz. So what we are talking about? So if there exists fz dz and there exists something, let's say z naught, where the function is not analytic, and you are trying to figure out the integral of fz dz over this C, then all you are supposed to find out just this a minus 1 term, and this a minus 1 term came from our Laurent series expansion. So a minus 1 term, if you think about in the Laurent series expansion, this is the coefficient of 1 over z minus z naught term. So we do not need to worry about any of the term on the left or any of the term on the right. We just need to figure out what is the coefficient of 1 over z minus z naught and we are done. So several problems of complex analysis in terms of integration is just of finding out residues. If we find out the residue, whether it is from our this one over z minus z naught coefficient or some other method, then we basically find out our result. It's rather interesting. And this is the power which Cauchy used to come arrive at the Cauchy residue theorem. So this is the whole idea which comes here, that a minus 1 term which is residue, if I multiply it by 2 pi I, it gives me this. This is the idea. Okay. And this also gives the famous residue theorem. We will just have the example soon, but the example says that instead of one, this if you have plenty of these guys, the singularities. So fz dz, if I have to find out, then that can be written as simply 2 pi I summation over all of these guys, j is equal to 1 to k. So let's say 1, 2, 3 singularities, and we have k such singularities, and this is nothing but residue z is equal to z. So finding out integral which includes all the singularities or whatever number of singularities is equivalent to finding out just the residue of the function at zj, and this is nothing but the coefficient of this term 1 over z minus z naught or 1 minus z. That is it. So this is something. Remember that what we are talking about, positively oriented, containing z1, z2 up to zk. In case if some of the z's are outside it, then of course, then in that case, of course, you do not need to consider those of z's. So in case if the function does not, if the path, the contour does not include any of the singularity, then what will be the result of this?
0.
It will be 0 because there doesn't exist any singularity. So that means that you won't find any coefficient of 1 over z minus z naught because there is no term like that. So if you think about it, the Cauchy-Gaussian theorem, we are expanding Cauchy's Gaussian theorem. Earlier we were considering function fz which was analytic, and if the function is analytic, then over a positive oriented path or even the negative oriented path, the integral was 0. The Cauchy residue theorem extends the reach that even if the function is not analytic everywhere, and if there exists certain points, let's say 1, 2, 3 up to k, so finite number of singularities, then in those cases I can find out the integral result just by doing this 2 pi I times this one. So Cauchy, look into it, which is very interesting. We started with Cauchy-Gorset theorem. We went up to Cauchy integral formula and the extension of the Cauchy integral formula. We use those formulae to say that we have the Laurent series expansion. In fact, the Laurent series expansion proof is basically coming from that. After having that Laurent series expansion proof, we discussed about the singularities, and we are now again going back to evaluating our integrals and saying that the Cauchy-Gorset theorem is now extended to include our singularities. So there is a chain of events. If you look into it, it is a very nice and logical chain that Cauchy-Gorset theorem, Cauchy integral formula, Laurent series expansion, and Cauchy's residue theorem. One after another, it will come naturally if you go. Because all you are trying to ask a question that what happens if there doesn't exist any singularity inside it, and what happens if the singularity exists inside it, how will you have the integral of the function? So this is all you are doing, and the power is in terms of that. Okay, the best thing is let's just do one integral or two integrals and let's move further, because Cauchy residue theorem, it is one of the most important theorem in terms of solving integrals. Let's just do something. We expanded example 1 over z cube minus z4. We expanded this function. We tried to even find out the Laurent series expansion about z is equal to 0 and z is equal to 1. The good point about in online classes that I can tell you that we have done that. Otherwise, it would not have been written on board. But yeah, I mean, we saw that, right? I mean, we did this expansion. Now I can extend this question, whatever question we asked. Fun. What are the singularities? Are there singularities in this function fz? This we already said, yes, there exists z is equal to 0 and z is equal to 1. What kind of singularities they are? So if I ask a question, what is the nature of the singularity at z is equal to 0? What
Pole
will
of
be your
order
answer?
3.
Order
It's a pool of order 3.
And how did you answer so quickly? Because
So in
the expansion is in front of you, right?
the maximum power of 1 over
1
z
over
term
3.
is 3.
Maximum power of 1 over z term is 3. And that is how you have said that this is a pole of order 3. Can you tell me what is the singularity, nature of the singularity at z is equal to 1? From this expansion, the one which is written in the bottom. Yes, no.
No, sir.
No. Because
No,
it
sir.
is not expanded about z is equal to 1. This is expanded only about z is equal to 0 in the entire region, right? So you will have to expand it around z is equal to 1. So can you expand it and tell me? In the meantime, I frame my question. Can you just check? Z minus 1. So it is taking time. Okay, then homework for this. Maybe we will discuss it in the next class, additional class, nature of singularity. So this is pole of order 3. And that is good. Good. Okay, so let me frame the question which I want to solve. The question is this. I want to find the integral of this function fz dz over a contour which is positive closed circle about z is equal to 0 with radius half, mod z is equal to half. So how will we solve that? We will solve it by using, yeah, right. So this, but before that you have to say something about how are we using the Lorentz series. Why are you using the Lorentz series? Because you are going to
Because the
invoke
singularity present inside the
Singularity.
circle.
right, and you are going to invoke first Cauchy residue theorem to say that this integral should be equal to 2 pi I times what?
Residue.
F.
A minus 1.
F of z equal to 0 only. See, there exists two singularities, right? In general, if I say residue of this function, it doesn't make the answer complete because there are two singularities. Which residue are we talking about? Z is equal to 0 or Z is equal to 1 or both? Because if we are going to talk about both, then we will be talking about 2 pi I residue at Z is equal to 0 plus residue at Z is equal to 1. Are we talking about this? Or we are talking about 2 pi I residue at Z is equal to 0 only, or 2 pi I residue at Z is equal to 1 only, or in fact none of this. Which of these we are talking about?
0 only, sir.
And the reason is,
Because the singularity exists inside the cell. The
please
radius is
see,
half actually.
right, please see the question tells you that the path which we have to consider is a path like this with radius which is only half. So there exists only one singularity within it. The other one at z is equal to 1 is outside this singularity, right? Which means that you are not going to consider that z is equal to 1. And hence, what you said, of course, makes sense. You understand how to solve the problem. But all of you, I mean, since there is a class, all of you, please, you should remember the question does have this C, and the knowledge of C is very important. In fact, by this time, you know that C does not need to be a circle. I could have given you any arbitrary figure here. And in that case also you would have invoked what? To say that I can reduce it to my circle. So if let's say I would have given you any arbitrary figure with this maximum reach up to some value, let's say 3 by 4. So mod z 3 by 4. Then in that case what you would have done?
The path transformation of
Deformation of
contour.
contour.
Right. So you have done the path deformation, and you would have you said, sir, I can actually consider anything. I do not even need to think about half. I could have considered anything which includes 0, and that's it. I'm done. So okay, let's now solve this. So we are supposed to find out 2 pi I residue of function f at z is equal to 0. So what is the result? So 2 pi I, let's say a minus 1 for z is equal to 0 only. And hence somebody said that we are going to use the Lorentz series expansion. Please use the Lorentz series expansion and tell me how are you going to do that. So if you need the series form, I have it somewhere, right? Here it was. So what is the residue?
1.
1. Very good. So let's just write down and see what should be the answer. So it will 2 pi I. Residue of this is just 1. So your answer is 2 pi I, and you are done. All you have done is basically you have checked the coefficient of the term 1 over z. You did not need to check anything else. Had I asked you the same question and I would have asked negative oriented circle, which means the circle which is getting traversed the clockwise direction. It includes still this, the radius is still half. In that case, what would have been the result?
Minus 2 pi.
Negative of 2 pi I.
Minus
Great.
of 2 pi I.
Minus 2 pi I. Right. What if the semicircle is there and traversed positively in the upper half, let's say?
Only pi I
Negative
Pi.
semicircle.
with a negative sign.
Right.
Minus
So
pi.
please see that we are invoking our knowledge of contour integral or line integral in the sense that we know that if it is traversed in the one direction, then it is same as negative of the traverse in the opposite direction. There is similar result which we use in our real analysis or the real integrals also, but make sure that you remember that. Hence, I ask my students to look at the C very carefully because one, whether it is positive oriented, negative oriented. Two, whether this includes any of the singularity. Because if it does not, then the problem is over at that point, very point. So two, it takes care of that. Third, please also look in terms of sometimes the question asks how many times this guy is getting traversed. Instead of one, it says that it is traversed twice or thrice or 4 times. In that case, you are going to multiply this 2 pi I with that number, the number of times it is traversed. So, and if it is traversed twice, then you will be multiplying by 2, traversed thrice, you are going to multiply by 3, so on and so forth. So, the same question with difference in C, of course, results in the different answers. Hence, make sure you understand this importance of the path which you are using. Yeah. So I know most of you understand this importance in terms of the radius or whether it includes singularity or not. But don't forget about looking at whether it is positive, negative, or half semicircled or not. So those things also matter. Let me just give you a very quick homework problem. For example, integrate fz dz, where fz is equal to z e 3 over z around, let's say, okay, does this have singularity?
Yes, sir, it will have.
At, so this is 3 over z,
Z
not 3 over
equals
Z
0.
z equals 0. So does path include singularity?
Yes, sir,
Yes.
it does.
Okay, yeah. And what kind of singularity is there?
Essential.
Sir, is it essential?
Think about it. Exponential 3 over z.
Shell. Yeah, essential.
It has to
Essential.
be. I mean, you know the expansion of exponential z, so it is z plus z, 1 plus z square over 2 factorial plus z cube over 3 factorial, so on and so forth. So there will be infinite terms of the type 1 over z. Even if you are multiplying by single z, it is not going to change that. And all you need to worry about a term which is of the kind 1 over z, right? Because it has only one single isolated singularity at z is equal to 0. Nature is essential, but in order to do this, you are going to do 2 pi I residue at z is equal to 0 for this function f set, and you are done. Yeah. Thus we understand that finding out results for our problems is mainly finding out residue. So some of the quick residue related results, which is particularly important for poles. For essential singularity, Lorentz series expansion is the best, since it's easiest to figure out, write down the expansion and then do that. But for poles, there exist several formulae. So for example, if it is a simple pole, So let me just give some number. Fine. At z is equal to z naught. And I am supposed to find out residue of the function. So fz has a simple pole, which is basically our a minus 1. Then the result can be as simple as limit z tends to z0, z minus z naught times fz, and you are done. So all you need to do is to multiply z minus z naught with fz and take the limit. And from where it is coming? It is coming from this knowledge. 1 minus z naught is this. So your function is of the kind this. A1 z minus z naught plus so on and so forth. Yeah. If you multiply it by z minus z naught, then what will be this? This will be a minus plus a naught z minus z naught plus a1 z minus z naught square plus so on and so forth. Right? There cannot be any term of the kind 1 over z minus z naught square because it is a simple pole. Yeah. So this is the most term which is possible. And if you now take limit z tends to z0, then what will happen? Z minus z0 fz.
All the terms except a minus 1 will go to 0.
All the terms except a minus term will go to 0, which means that finding out residue at z is equal to z naught for a simple pole is as simple as doing this simple one. Limit z tends to z naught, z minus z naught. Good. What about if I say pole of order m? Yeah. So you have, I mean, if you remember, we wrote like a minus m, z minus z naught m, plus a minus m plus 1, z minus z naught m minus 1, plus so on and so forth, a minus 1 plus over z minus z naught. And of course, you can write down a 0 and so on and so forth. This kind of a function. And I ask you to find out in the similar style, residue at z is equal to z naught of this fz. How will you find out?
So multiply it by z minus z naught to the power m.
So multiply it by z minus z naught to the power m, and let's say I took fz, and then what?
So then take the limit z tends to 0.
Is that the solution which you use for a finding out the residue? You have found these residue, right? I mean, this is something which you have done in your BSc. Answer is coming from
So
there.
we do the derivative.
So you do derivative how many times?
So m minus 1.
-1 times.
Because what you are interested in is getting power 1 over z minus z naught, and this interesting point only for your higher order poles, that you are going to take this derivative m minus 1 times, then you are going to take your limit z tends to z naught, and in fact even this is not done, you did 1 over m minus 1 factorial. So please see, so now I should remove this. Check this formula for your simple a minus 2 z minus z naught square plus a minus 1 z minus z naught plus a0 this. Please check this formula and see what do you get. Yeah. Finding out residue of z is equal to z naught at fz of the function at this point, for which is a pole of order m, is actually using this formula which I have written 1 over m minus 1 factorial limit z tends to z naught d m minus 1 dz m minus 1 z minus z naught m times fz. So this is what we are supposed to do in that case. Yeah, that's interesting. You will tell me The only place where I am leaving it so that I will ensure that you are going to check it, whether I should be writing fz or I should be writing fz not. So this is the only question which I am raising, and in order to check that, you will of course have to either solve this one or figure out from book that whether which formula we are going to use. So this is the only point which I am leaving you. So can somebody tell me quickly whether you use fz or whether you use fz not? No? So you are
So we
going to
use
check.
FZ only.
Okay.
Yes, you.
So you use fz only, huh? Yeah. So okay, I hope you all agree. You all are right, but please still check it because you are going to use these formulae a lot, and hence I say that please look into it. It's important, and I will
Like
just
we would use
you would
exit
use.
not the use of the putting limit.
Yep, yeah. I mean, you put the limit immediately after that. Sure, limit z tends to z naught. So there is no point of using f z naught here, right? I mean, this is what you are trying to say.
Yes, sir.
Yeah, I mean, it does make sense. I'm just asking. It's a curious question that whether you recall, you are able to recall, or are you able to make a connect. It is not important that you are able to remember the formula. It is just important whether you are able to make a connect. And this simple one will just tell you why will you use this kind of a formula for residue. Although of course it can be done very simply for this itself, but we'll have to take many derivatives here since we are doing this derivatives so many times. There is one additional one, which is the third one, which is where I will leave at this
Sir,
point. Yes. Just let me
sir.
just write one more and then I'll let you ask question. Is it fine?
Yes, sir, sure.
Yeah, thank you. So for simple pole, again, the one which we have already done, this was formula number 1, which we use. If function is of the kind pz over qz, where we both are polynomials. So this is polynomial of z and this guy is polynomial of z. But this guy has to have degree at least greater than equal to 1. So it cannot have degree less than 1. So it cannot be a constant. Yeah, it has to be a polynomial with degree greater than equal to 1. And if pz naught is not equal to 0, so that we know that qz is such that it is a simple 0 at z is equal to z naught, but pz naught is not equal to 0, then finding out residue for this guy wherever we have the polynomials, which is residue z is equal to z naught, pz over qz. This is equal to saying that we are finding out p of z naught divided by q prime of z naught, where q prime of z naught is nothing but dq over dz with z is equal to z naught. So this is another formula which becomes useful when you find out that there exists a simple pole. You can use part 1, I mean there is nothing wrong with that, but you can also use this if there is a ratio of two polynomials. The denominator, the polynomial has degree greater than equal to 1, so that you can take the derivative, I mean you will understand that, and your numerator is not 0 at that z is equal to z naught. In that case, you can use this formula also, which is commonly used by some, and this becomes very useful if polynomials of very high degrees come and you do not want to factorize it. But then there has to be something that if it is very higher order ones, then will that be a simple pole? So somehow the formula will be valid only for simple pole and for nothing else. Yeah, I mean, it is great to do these derivations. It is just that we have limited time to finish our complex analysis, and I do not want to take time out of my group theory, which is also something which is very important. And hence, I am giving you just the formula itself. The formulae are simple to derive, they are not very tough. But please remember that we can use these three simple formulae for finding out the residue, other than just finding it out from the Lorentz series expansion. Now the question you want to ask. Please go ahead.
So the second residue formula I was talking about.
Yes.
Yes,
Yes.
so I think that we use f z is equal to z not after doing the all this the bracket
Yeah,
thing.
that somebody else also said that, sir, what is the point of taking the limit z tends to z naught here if we were to invoke f of z naught here? Yes.
Okay.
Yeah, I mean, somebody else. I just said that please do confirm it by looking at the text, some text, so that you see the whole formula coming up. In principle, I am asking you to go through your simple derivations which you have done to figure out this. But yeah, if not, then at least do this much so that you remember these formulae. And I told you that in the examination, we are interested in probing your analytical skills of solving problems using these methods. So it will be limited to that. We are not going to ask you to derive it. And anyway, derivation is commonly given in almost all the text, and it is an open book examination. So we are not going to give derivation for this kind of a problem anyway. Questions? Okay. So by the way, residue theorem has a statement, and the statement is if the function is analytic inside and on a contour which is positively oriented, containing finite number of isolated singularities, one z1 to zk, then the integral of fz dz is equal to 2 pi I j is equal to 1 summation k residue of this function at those ones. So of course there is a statement, I just did not say it. However, I hope that over the period of time, the way I have been explaining things, it is entirely clear to you that we are going from the direction of, first we were trying interested in figuring out whether there are functions for which the integrals are path dependent or independent. We find analytic functions, and then we are interested in figuring out that even if the function is non-analytic at certain points, are we able to find the integral? And we are still able to find the integral using our Cauchy residue theorem. Okay, so we will meet in our next additional period, and I will start using this residue theorem to find out certain definite integrals. So it will of course involve some calculations and doing actual integrals. Fine. So in the extra class, we will start using residue theorem to solve certain integrals, the definite integrals ones. Yeah, which will be at 2. So thank you guys. In case if you do not have any further questions.
Thank you, sir.
Thank
Thank you,
you.
sir.
Yeah.
Thank you, sir.
So,
Yes.
सर जो आपने अभी होमवर्क का क्वेश्चन दिया था उसमें
हाँ.
एसेंशियल सिंगुलैरिटी है सर
हाँ.
तो सर उसमें
Exponential.
हम रेसिड्यू कैसे निकालेंगे उस केस में
Oh, I mean this is something very simple. अगर आप सोच पाओगे तो सी अगर आपके पास एसेंशियल, ये तो पोल्स के लिए मैंने आपको बताया है ना.
यस सर
In case if there is, let's say, think about this exponential 1z. हाँ, अगर आपको इसके बारे में सोचना है, so what is the expansion of this guy? 1 plus 1 over z plus 1 over z square 2 factorial plus 1 over z cube 3 factorial, so on and so forth. This is an essential singularity at z is equal to 0, right?
यस सर
So finding out residue is saying that we are going to find out coefficient of the term 1 over z minus 0. So you are going to do Lorentz series expansion in those cases, and you are trying to figure out the coefficient of that. Yeah.
ओके सर आई थॉट जो मैक्सिमम पावर होती है हमें वो वाली देखनी होती है
मैक्सिमम पावर बिल्कुल देखनी होती है, जब तक पोल है वो मैक्सिमम पावर तभी तक है. जैसे ही आप एसेंशियल सिंगुलैरिटी, जस्ट द वे यू सेड इट एंड सिंस आवर क्वेश्चन हैड इट, सो मैक्सिमम पावर कहाँ पे रुकेगी? Infinity way.
सर
So you
इन्फिनिटी
cannot, yeah, which means you cannot use any of the methods which I mean any of the particular methods which I have said. 3 that was pole, 2 that was pole, 1 that was pole. So you will be able to solve questions of the pole in this way, but you won't be able to solve questions of the essential singularity in that way. Sure. So you'll have to think about the
ओके
Lorentz series expansion. In fact, some of the times a function has pole as well as essential singularity. So you will figure out that you will solve half of the problem using your method of the poles and half of the problem. So you have to find out two residue, for example. One residue will be for a pole of some order and another residue will be for essential singularity of some. So essential similarity will not be of any order. So you'll have to expand the series. You'll have to do the series expansion. You'll have to just come up with the coefficient of 1 over z minus z naught. Good question. I mean, this is why I actually gave this question actually. That you will figure out that none of the formula which I have given, that can work.
एंड सर इसी फॉर्मूले में अगर
Thank
z इज इक्वल टू ई रेस्ट पावर 3/z है सर, इसे हम पूछा जाए कि एनालिटिक प्रूव करो, तो सर वो कैसे करेंगे?
Analytic कैसे prove करोगे? मतलब what is analytic? Analytic means closed form expression you want to get. The closed form expression you are going to get. The questions are generally asked for the Cauchy residue theorem in terms of the applied problem, right? आपसे पूछा जाएगा कि ये फंक्शन है और इसका इंटीग्रल निकालो. Now you can say इसमें क्या होगा सर अगर मैंने z minus 1 स्क्वायर ये भी ऐड कर दिया, तो इसमें एक पोल भी हो गया, इसमें एक एसेंशियल सिंगुलैरिटी भी हो गया. या तो कोई मेथड यूज करेंगे हम लोग आगे जो हम डेफिनेट इंटीग्रल्स में लाने जा रहे हैं, otherwise you will have to use whatever I have told you. Nothing else can be used. You have to do
Okay.
the Lorentz series expansion. Yeah, there are no simple straightforward formulae like this, the ones which I have given, for example, for the poles. Okay. Yeah, revisit your concepts. I'm pretty sure that you would be able to do it. Okay, wherever you face problem, I'm there. Okay guys, now bye.